Hello, and welcome back to another session on data mining. Today, we're going to talk about different types of deep learning libraries. Now, we have covered basic neural networks like the multilayer perceptron. We've talked about how convolution neural networks operate, and there are some really nice libraries out there that allow us to code or implement these type of neural networks pretty efficiently, and they're able to execute for both training and inference these neural networks on machines that support GPUs or other architectures that accelerate the learning of the neural network or the training time of the neural network. So before we move on to different types of libraries, there are some commonalities across all of them, and I'm going to talk about those first. I've listed those on this particular slide. So all of these deep learning libraries, they essentially do these things. The first bit is automatic differentiation, and I'm going to talk about what that means exactly. They implement different types of optimizers. They allow the use of efficient hardware for multiprocessing, such as GPUs, and they support an efficient representation of the machine learning model. So if we break down our any machine learning model, you get representation, evaluation, and optimization. We first need to represent a deep learning model, so we need a library that can efficiently represent my machine learning model or my neural network without going like writing a whole lot of code for that. So we can implement all of the operations involved in a deep neural network from scratch in terms of matrix multiplications, but that's going to take a long time. So what we need is a way of representing a neural network with its training parameter or weights in a very abstract manner with minimum amount of effort. So that is the first thing that these libraries do. They support efficient representation of your machine learning model or abstractions for you to implement those machine learning models. We've already used some of those abstractions, such as the NN module in PyTorch. Keras is another great tool that allows us to represent neural networks and make neural networks pretty efficiently. So that is what this relates to. The second bit is evaluation. We need to have support for evaluating different types of loss functions. So these libraries support different type of loss functions built in. You can also implement your own loss functions. The third most important bit is optimization. When we are optimizing, when we have a loss function, what we want to do is we want to take the gradient of that loss function. So let's say you've got a loss function L that takes in an example X and the corresponding label Y. We have a loss function that takes in a prediction f of x, which is from a neural network with weights theta, and you've got a corresponding target y. And we want to minimize this. So the optimization problem that we are trying to solve can be written as minimize or find me weights such that the loss of all of these examples or the sum of these losses is minimized. Okay, so that's what we want to do. And the way we typically do that is we take the gradient of this loss function with respect to the weights of the neural network. Okay, and that means we need to do this differentiation bit. So this optimization step involves this differentiation. Now, what we have done in the past is that we have expressed this or we have written down the expression for a particular loss function or the derivative of the loss function by ourselves. We've calculated or hand evaluated what the gradient of the loss function looks like. But we don't need to do that with these libraries. If you have a loss function and if you have a representation of your machine learning model, and if both of them are differentiable, then these libraries actually allow you to implement this implicitly or automatically. So you don't need to write analytical expressions for these type of derivatives. And the next step they do is that they're able to use these gradients to perform optimization. So when, for example, if you want to perform gradient updates, this is what we typically want to do. We want to take steps opposite to the direction of the gradient, and they implement not only gradient descent but other type of even more efficient optimization methods. So this bit, automatic differentiation, is a huge help because all a user needs to do now is they need to represent their model. They need to present the evaluation of the loss function, and then the optimization is taken care of automatically by most of these libraries. And not only that, they are able to do it very efficiently on specialized hardware such as a GPU, for example. Uh, so if you're not familiar with how GPUs work, GPUs are efficient computing machines which are originally developed uh, for doing graphics processing. But now we use them for general purpose, or these are called GPUs. And what they do is they have multiple cores, thousands of small cores or computing cores, and each of those computing cores can work together with the other cores in that GPU to accelerate this optimization step. So there's a lot of multiprocessing going on, and most of these libraries support the execution of your code on the specialized hardware. GPUs are just one of them. There are other ways of accelerating your code as well, and there are more and more different type of hardware coming up that is specialized towards deep learning. So most of these libraries support all of these things. So they essentially minimize the amount of pain that an implementer has to go through, or a coder has to go through, in order to realize a particular machine learning problem. Okay. Now there are different variants. My favorite one so far is PyTorch. It implements an imperative programming platform or a philosophy in which you write your code, but you can stop the execution of your code and check what the variables are at any time. Uh, Understanding what dynamic computer graphs are requires a bit of knowledge about how automatic differentiation works, and I'm going to touch on that in just a bit. But what these methods typically do is that they express the computation that you want to do in the form of a graph, and then they allow massively parallel execution of that computation graph and computing gradients and so on. And it's very flexible. It's a great research tool. However, if you want to go for production grade machine learning or deep learning, there's plenty of good support from TensorFlow. It has very good documentation. It even supports TensorFlow.js that allows you to run your models in your browser, and that's a pretty good tool if you want to deploy a particular model. It's symbolic. You first of all, the original versions of TensorFlow required you to write all of your code much like in Java, and then compile that, and then your model will be executed even within Python. And that had the static computing graphs, but now that has been updated as well. So TensorFlow is another very good library. Keras is a library that allows very good representation. It can use either TensorFlow or PyTorch or another such library in the back end, and all you need to do is to define these neural networks in Keras, and then all of that is taken care of, the optimization bit, and so it's more closer to the scikit-learn style machine learning model development that we have done. There's also Cafe, Theano, and these days I'm exploring these two libraries, JAX and Julia. These are really upcoming, and they're gaining popularity because they offer some really nice properties. Especially the one in Julia, it allows native support for code execution on GPUs. So that's pretty awesome. So this is a very high level overview of the different types of deep learning libraries out there. It's really important to understand that what are the requirements for a library. It needs to have these four things in place: automatic differentiation, optimization, efficient hardware utilization, and efficient representations and abstractions. Now, what we are going to do is to discuss in a bit more detail what is automatic differentiation and how does it work. Typically, you don't need to understand this when you are writing code, just like you don't need to understand how a transistor works in order to use, let's say, your cell phone or something. But it's something, it's good knowledge to have that in and to have at least a high level understanding of what's going on in the background when you write your machine learning models. Okay. So one of the best things about these libraries, all of these deep learning libraries, is that they support these automatic differentiation. Now, what does that actually mean? Let's say we've got an expression like this one: E is equal to A plus B plus 1, and A or B are the two parameters, two variables that affect E. Okay, and we can expand this in this form, and then I can go ahead and calculate the partial derivative of E with respect to A, which in its analytical form comes out to be B plus 1. Okay, so if you take the derivative, there's going to be over here, and then there's going to be 1 from coming from this, and we can evaluate that particular derivative at a given point. Let's say if a is equal to 2 and b is equal to 1, then this partial derivative, or partial e or partial a, comes out to be 2. Similarly, we can take the derivative of this partial e over partial b, and that comes out to be 5 for this particular value of a and b. The analytical solution comes out to be a plus 2b. So this is how you would manually do differentiation. Now, one of the best, so some people relate that the success of deep learning is only because of we had GPUs, and that is definitely a very useful piece of hardware that allows us to execute these models in parallel, and it's a huge step forward. But it's not the only thing. At the core of these deep learning libraries is this automatic differentiation ideology, which is a suite of algorithms that allow us to generate the derivatives of a given expression, any expression, with respect to its parameters. So in this particular case, the expression that I have was e is equal to a plus b, b plus 1. And then what I can do is I can take these derivatives with respect to a and b. And these automatic differentiation algorithms, or as they are called autodiff algorithms, what they do is first they represent your computation in the form of a computation graph. So for example, this particular computation that we had can be expressed in the form of this computation graph that we have over here. So we have a plus b, and we assign it to a value c, and then we have b plus 1, and we name it d, and these names can be arbitrarily chosen depending upon the type of graph method that you have, or graph representation method that you have. And then we're taking the product of these two, which constitutes our final variable, which is e. Once you have a computation graph like this, what these libraries do, these autodiff libraries, is that they implement some very efficient type of automatic differentiation. So I can, if this is my variable of interest that I want to take the derivative of with respect to a and b, then I can do that in a single pass. And this is done using something called reverse mode auto differentiation. I'm not going to go into the details of that algorithm, but these algorithms were developed back in the 70s, and they form the core of, or the algorithmic core of all of these libraries. Now, it's possible to use PyTorch to do this, and this is what it does. So we first of all initialize two variables, or the two parameters that we are interested in. So we want to take the derivative of e with respect to a and b. So we will first declare these two parameters a and b, and notice that we have a specialized type of these. These are floating point numbers, but they have a gradient associated with them, and that's why we specify a dot requires grad true and b dot requires grad true. So these are not constants. We'll be calculating the gradients of an expression based on these two parameters. We write the expression e, which is a plus b into b plus 1, and all I need to do in order to do all of this is simply call e dot backward, and that's what is going to implement that efficient reverse mode automatic differentiation. There are even better algorithms coming out now, and what this does is that now we can calculate what the gradient of e with respect to a and b is, or the derivative of e with respect to a and b is, and we can get exactly the same values. So I welcome you to execute this piece of code so that you can understand the role of automatic differentiation. Notice that while we wrote this code, we didn't write the expression or the analytical expression for the derivatives. All we did was write the expression of what we wanted to do, and then the automatic differentiation is automatically taken care of, or the differentiation is automatically taken care of. So that's the power of automatic differentiation. It's a suite of algorithms that allow us to calculate the derivative of any computable expression, as long as it makes sense to take a derivative of it, and we can execute, we can do it automatically. Okay, so if we have an initial value guess, we can change these, we can change a and b, and then we can re-evaluate what the impact of that is going to be on this derivative. It's really easy to do. Now, what does that have to do with neural networks? As we discussed, neural networks involve taking the derivative of the loss function with respect to each and every weight of the neural network, right? That's what we want to do, so that the next step, the optimization, can then take place. So what we do, or what these deep learning libraries essentially do, is that they represent a neural network just like a computation graph. So if you think about a neural network, what do we do? What does a single neuron do? It takes in these inputs from, let's say we've got x1 up to xd. We have the corresponding weights w1, w2 up to wd, and then we've got a bias term which is whose input is always 1, and then you've got a b term over here, or let's call that w0, just for so that we can use the same notation. And what a neural network does is it first performs w transpose x and then applies an activation function on top of it, right, to generate the corresponding output. And then we have the loss function, which is, let's say, so I should be calling it f of x rather than y. So a loss function is simply f of x comma y, which can be, let's say, y minus f of x squared. Okay, this is a very simple loss function. We can have y minus sigma w transpose x squared. Now this is a loss value, and what we want to do is to take the derivative of this loss with respect to the weight values that we have. So we need to do automatic differentiation. However, if you look at this expression, it's nothing but this is sum of products. This is another function applied on top of it. This is going to be a constant for a given value of x. And all we need to do is to take a derivative of this with respect to of this expression, of this loss expression with respect to all the weights. So this is nothing but a simple computation, right? Much like computation that we had over here. And what these deep learning libraries do is that they represent the computation of underlying the neural network that we have as a graph, and then we can do automatic differentiation on top of it. And this can be coupled with very efficient optimization packages so that we can find optimal values of the weights. So what these deep learning libraries do is they represent a neural network loss calculation as a computation graph, and then compute the gradients and then optimize. Okay, so we're going to see how it's done for a single neural network, for a very simple neural network that has 2 layers, and we're going to break down each of those parts. So we first write. Now remember, the first good thing about a deep learning library is that it allows us to write or express or represent a given machine learning model. And this is what I'm talking about. This is an abstraction that I don't need to define what nn.linear is. It's already implemented in there. It's nn.sigmoid already exists. So all I need to do is to piece these pieces together and express them in the form of a computation. So I develop a model, which is a sequential model, and we have the 2 neurons in the first layer, followed by which each of them is acted upon by an sigmoid activation function, which is passed to a neuron, to a single neuron, which and its output, and also has a sigmoid activation function which generates the final output. So the first thing that we need to do is express our model, which we have done over here. For a given input x, we can compute the corresponding output, which I've called z over here, by using model of x. So this is in PyTorch. Other libraries are pretty similar, and they do something very similar, each one of them. What happens next is we do the loss evaluation. We have a corresponding target y. We calculate the loss using a loss function. There can be different types of loss functions which are already implemented or available within these libraries. So we have the representation bit, we have the evaluation bit, and once we have that, we want to take the derivative of this loss function or this error function, excuse me, with respect to these weights. But where are the weights? We don't see any. Now those weights are actually, if you think about these, if you express this in the form of a graph or a computation graph, you'd be able very easily see those weights. So for a given input x, let's say the input is 1, 0, the first thing that happens is a dot product with 2 neurons, right? So each of those neurons receives each of these inputs. So we have got 2 inputs, we've got 2 neurons in the hidden layer and a single neuron in the output layer. And this is what happens. Each of the inputs, each of these hidden layer neurons receives its inputs, okay, and from each of the features, and then each of these neurons multiplies the corresponding input with 2 weights that it is associated with. So if we can write that in the form of a matrix, so let's say if you've got an input 1, 0, the first neuron can have weights 3, 4. If you initialize it that way, the other neuron has 2 weights which are 2, 3. And once we do a dot product of these, and we can do that. We can add a bias term that is corresponding to each one of these neurons, and that is the bias addition taking place. We get the net input net output of this neuron, each of these neurons. So now we have two outputs. The first neuron produces 0.73 and the other neuron produces 0.11 in this example. And once we have that, we can pass that to the next neuron, which is a single neuron. And what it does is also computes a dot product with its own weights, which are 5 and minus 5. So there's 5 here, minus 5 here. And then that product, we add a bias term to that corresponding to this particular neuron, and we compute the sum, and we apply a sigmoid function on top of that, and that's how our net output is computed from this neural network for this particular input. Let's say we know the target for that particular input, and we can compute the loss function. So once we have computed those loss functions, we can take the derivative. So this is where the weights come in. When you specify nn dot linear, essentially what you're doing is initializing a matrix like this one and a corresponding bias term like this one. So that it initializes the biases and the weights. So in this implementation of these neural networks, it's actually the layer of weights that we initialize, not the layers of neurons. So we have a layer of weights of two neurons. Each of them has two weights because we have two features, and then each of them, their output is passed on to a sigmoid function, and the next neuron, there's a single neuron weight vector over here with an associated bias term. That's what this line does. So that is where the weights are hiding. And once we've computed this, so when you write this code in PyTorch, this is what PyTorch looks at it like. There's a computation graph, and once you have a computation graph, automatic differentiation can be done. And this is how you can do that. All you need to do is do e dot backward, and all of these weights are now the parameters of this network, and you take the derivatives of your loss function with respect to these weights. And this is completely done in an automatic manner. Imagine if you had to write expressions for each one of those derivatives, it would have taken really long, but this is really useful to have. So once you have this, you can implement gradient descent. So weight, the new value of the weight is equal to the old value of the weight minus the error derivative. So this is what this does. You can implement gradient descent yourself, but there are also built-in optimizers, and you can use those. And that's pretty much so. In this case, for example, we're using an ADAM, or adaptive momentum-based adaptive learning rate with momentum optimizer. And I'm going to talk about that in just a bit. And you can execute this process many times. So this is what happens once you initialize a neural network in PyTorch. This is the underlying under the hood view of how these libraries operate. Each one of them has roughly the same ways. Some are better at representation, some have good optimization tools built into it, some are more efficient than others. But PyTorch is a good compromise in terms of all. If you have a good research-based need, if you want to be more flexible, it's a really good library. TensorFlow is another good one. All of these libraries have essentially work in the similar manner. So once you know this philosophy, you can pick any one library that you like. Okay, and these libraries, as I said earlier, have different type of optimization methods built into them, and this computation graph and this optimization is done or executed in massively parallel fashion if you have the right hardware like a GPU. So that's what this does, and so these can be parallelized in various ways. And I'm not going to go into the detail of how that is done, but for your understanding and implementing machine learning models, you need to understand that these are executed in parallel. These gradient computations are done in parallel on your GPU, and there are different types of optimizers available. You can have your gradient descent optimizer, which essentially says always go down. You update your weights in the direction opposite to the gradient with a learning rate of eta. And what you do is you take all of your data set, you take the derivative of that with respect to you take the derivative of your loss function with respect to the weights for the whole of your data set, and you take a step. A slightly more efficient version is what is called stochastic gradient descent, in which you pick a particular example at one time. This is an extreme case of stochastic gradient descent, and you use only that example in your loss calculation. and you take the derivative of that loss function with respect to the weights, and you take a step. So notice that there's a difference over here. We're taking the derivative of this with respect to only a particular example. Now you can also do that in a mini batch fashion. You take a bunch of examples, that as much as you can fit into memory, and you can take the derivative with respect to that, and you can execute that. And this is typically the way these optimizers are used in these deep learning libraries in a mini batch manner. There are also stochastic gradient descent with momentum. So remember, if you have a optimization function that you want to find the global minima of, and you are, let's say you're currently over here, and you want to take a step in the direction opposite to the gradient, so you would end up from this location, you would end up to, let's say, this location, right? So that can be your next step, and this can be your next step, and so on. But as you can see that the global uh, uh, curvature of this optimization landscape is pointing downwards. So perhaps we can take longer time steps. We can take longer steps, sorry, as we go through this gradient descent. And this is what is done to improve the efficiency in these different variants of gradient descent. So you can have stochastic gradient descent with momentum that essentially accelerates your step size or increases your step size if you're going downhill for a long time, because that means if you have been going down for a long time, that means probably the next step is also going to be in the same direction. So this adds an acceleration factor based on your previous history. You can have a Nesterov based momentum which accelerates but not indefinitely. So there's an upper bound on how large your step size can be. There's adaptive learning rate by accumulating past gradients method, which is called ADAGRAD. There's also ADA delta and RMS prop, which are essentially adaptive learning rates but does not accumulate all past gradients. And the one that we've been using is called adaptive learning rate with momentum. So it combines the idea of momentum with an adaptive learning rate. So your step sizes are automatically adjusted depending upon the curvature of the optimization landscape. So you can end up with better convergence. And each of them has their own pros and cons. Not one of them is better for every problem, which is visualized in this beautiful visualization that has been created over here. And as you can see, starting off, start it again. You can see that different methods take different times to converge to the global optima. The blue curve, which is ADAGRAD, is still is probably, sorry, the red one, the stochastic gradient descent, is the slowest one in this case for this particular problem. There are some methods that actually overshoot the optima and then they converge back. Remember, the loss landscape of a neural network is really complex. So the choice of the optimization method and its parameters such as learning rate or momentum parameters can have a huge impact on whether you would be able to achieve convergence. So it's always a good idea to analyze the convergence graph. And TensorBoard is in PyTorch is something really useful for that. It allows you to visualize your loss functions while you're training your neural network. Okay. So with that, ends our discussion on the various type of deep learning libraries. Remember, they offer automatic differentiation, efficient optimization methods, and an abstract representation, and they can execute your code on GPUs or other efficient computing platforms that are massively parallel. Thank you.